Okay, so I'm gonna create a polynomial that has the same seventh derivative, so it's got that seventh derivative. What is the integral of -1? Negative x plus c. How am I gonna solve for c? Sorry guys. I think it's better to have the windows open and put up with the emergency noise, but maybe not. Good times. What do you think, George? Should we close the window? Just yours?
It's fine.
It's fine.
Jesus
Closest. Is it going to last? Are we about to have like the evacuated because like my friend just retired. I used to get these texts. Oh, by the way, this is coming to your school in about 2 minutes. He always knew in advance. But he's retired, so I don't get that tip off anymore. Like I hear the noise and be like, hold up. Not anymore. Okay, so how do I figure out what this plus c is? Well, the sixth derivative, I want the whole thing to be 0 when I plug in 0, so plugging in, that's going to end up being 0. Integrate again, my polynomial's fifth derivative, negative x squared over 2 plus another c. Plugging in 0 here, I want it to come out to be 1. I'm doing stuff wrong. What is my c value going to become? When I plug in 0, I want this to come out to be 1. What does c sub 5 have to be? Well, okay, let's see. I want this 1 to equal negative 0 squared over 2 plus c. What is, so c is, sorry, yes, you said 1. So that's going to be a 1. Integrate again. Raise the power, divide by the new power, plus raise the power and a new c value. Plugging in 0, that's going to go to 0. Integrate, negative x to the 4th. Keep integrating. Oh my goodness. Raise the power. Oh. This C, plugging in the 0 zeros. See, sort of a pattern. And the first derivative of my polynomial oh my goodness. 4, 3, 2, 1. And plus C. Oh, goodness. Now in the end, the last one, the polynomial that's going to look like sine. I'm going to write it in reverse. 1 minus x cubed over 3 times 2 plus x to the 5th over 5 times 4 times 3 times 2 times 1. Is there a shortcut way to say that? Factorial. Okay. Goodness. Totally the long way to go, but so I have sine x and did 7 derivatives, and I said, well, sine x is going to be like, sorry, the first term was 1x. So sorry. I didn't integrate my 1. And just a heads up, this takes 2 days to actually start clicking, so if you're completely confused, I'm sorry and not surprised. So y equals x, that's all by itself, that's pretty close. And in physics, sometimes the teachers are like, y equals sine x, just use x when it's between -1 and 1 radian. But we integrated and we got -x to the 3rd divided by 3 factorial. Did it get closer for a bigger range? Is it stuck between -1 and 1, or is it getting bigger? It expanded. Then we had plus x to the 5th divided by 5 factorial. And then we did one more, and it was -x to the 7th over 7 factorial. And now we're out off the screen. It is accurate that far. So did I create a polynomial that wraps around to become sine? Yeah, okay. So, yeah, Max.
Was choosing to do 7 derivatives just arbitrary? If you do more, it gets more accurate?
Yep.
Okay.
So, all right. So yesterday and the day before, we were able to create a series by saying if the pattern of the function looked like this, like if it was that, I could create the series just by saying, oh, the first term, I'll make it something other than 1 because I want you to realize it doesn't have to be that. So first term, and then the r value is x. Like the geometric was easy. Let's force it to look like this pattern of a over 1 minus r, and then first term and then multiply. Easy. Sine does not look anything like that. So then there's this method called Taylor series, which is do a whole bunch of derivatives. How many derivatives? Well, it depends on how tight you want that to wrap around the curve. My brother does missile targeting. 1, 1, 1. It's distressing. Anyway, but if I wanted a lot of accuracy, I do more derivatives and then I integrate out. And I forced this polynomial to have the same point of tangency, the same slope, the same curvature, and then the same jerk, snap, crackle, pop, all those derivatives. Okay, so we're gonna try this. If you guys did not finish like filling out the packet from 9.1, please at least look at the key that's posted online. Here's the 9.2 packet. There's a stack going around the room. Taylor. Yay. There he is. So, can you guys try and do this one with these numbers, which I'm not telling you what the function is. Did everyone get one? Or Sebastian, can you play one? Oh, did you guys get it? There are too many stuff. Alright, so you guys try the process that I just, in a very messy way, did with sine. You okay? Where did the voice come from? Kind of. And I am leaving the 4 times 3 times 2 times 1 to kind of get you to believe me and understand where these factorials are coming from. You would probably just have reduced along the way. And so polynomial that would approximate this mystery is 2 minus 8x plus x squared minus 2x cubed, and then 3x to the 4th? The last one is? Yeah.
Why did you start like p to the 3 primes? Like why did you start with like x plus 72?
Well, I'm starting with the 4th derivative, so jerk. Sorry, no, 3rd, 4th, snap. I want the polynomial to have the same 4th derivative. So the function was 72. I'm gonna make my polynomial to be 72.
Then what's the derivative?
I'm now integrating from here. So I'm going from the 4th derivative to the 3rd. Just integrating the polynomials. And then I had to add a plus c. And I am showing this stuff over here to be like, because at 0, that's pretty much going to be the c values, but not every function when you plug in 0 gives you a 0, so I'm just trying to, and if you make the center somewhere else, it's gonna be a pain. But, I wanted to do this the short way. That first term is the function. This second term is the first derivative of the function times x to the 1st over 1 factorial. This third term, sorry, the second power is the second derivative, 2 x squared over 2 factorial. This third one, I swear they're gonna go here. The third one was that third derivative, negative 12, x cubed divided by 3 factorial. Okay? And this guy was the fourth derivative evaluated at 0, x to the fourth over 4 factorial. Like, there's a pattern. Question? No? All right. So, at the bottom of the page, it says, is there some kind of neat general rule? So, I want the, I don't know, 7th term? What's the exponent on the x value gonna be? X to the 7th? What factorial is gonna be underneath? 7 factorial. And, what derivative do I need? The 7th derivative. And we'll say it's 0. These guys are gonna be centered at 0 right now, but if I wanted it at 3, I'd need to know stuff at 3.
What is it given?
Maybe. But here's the general, if you really want that. So if you want it centered anywhere, find the derivatives at whatever center you're looking for. This guy, it's no longer x, but x minus the center to whatever power over that n factorial. All right. So this time, look. So I want you guys to do the painful process, do all the derivatives, evaluate the derivatives at 0, and then get your polynomial. This 4th column, I don't know if it's useful or not, but if you wanted the space, there you go. derivatives, multiply by the power, lower the power, chain rule ended up still being 1. So I did those 4 derivatives, plugging in 0 into each derivative, I got 1, -1, 2, and -6, and then integrating up, I get this thing. But just to show you and recap, does this look kinda like A over 1 minus R? Yes, yes? So if I generated the series here, this is 1 over 1 minus -x, I would have gotten first term, then multiply by R, then multiply by R, then multiply by R. That's not the thing I wanted. Like, the thing that I was looking for the series for was natural log of x. If I integrate that series, or this function, I get what I wanted. If I integrate this, do I get x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4? Like, I get the same thing? Like, so this is one of the rare ones that I could have gone 2 different ways. I can do all the derivatives and create it, or I could have been like, this was easier. As soon as I see that it fits the pattern, I'm gonna go the easy way. Okay. Okay. This thing, just give you worse uses of vocabulary. Find a first degree polynomial. Naomi, what's a first degree polynomial, like, more commonly called? First degree is x to what power? X to the first. So I'm asking you to find a straight line. What do we normally say? Like, don't we normally say find a tangent line? So do that. Find the tangent line. Ooh, where is it centered? At 4? Okay, so do that. George, what's the coordinate that we're gonna try and find our tangent line at?
4.
Well, the function that we're trying to approximate.
14.
So, function we're approximating is the square root of x, so plugging in the center of 4, that's my coordinate. Okay. Stella, what is my derivative? So I can find the slope of my tangent line. Multiply by the power, lower the power, okay? Katie, what is my derivative at the center that they are requesting? So plug in 4 to the derivative.
-1.
So 1/2 times the square root of 4, which is 1/4. Nathaniel, putting all those things together, what's the coordinate of my tangent line?
Y minus 2 equals 1/4 x minus
Okay, and that's how we would normally leave it there. To show you how, like, if you had to create a Taylor series, I need the function at the center, well, f of 4 is 2, so still we needed that coordinate. I need the derivative, well, Stella already found that for us. I need the derivative at the center. And now the polynomial, the Taylor polynomial, they would say that polynomial of one degree is the function plus the first derivative times x minus the center to the first power, and I'm done. Is the tangent line thing equal to the polynomial generated by Taylor series? Yes, Tyler, no? Yes. It's all a matter of G. One is solved for Y, one is not. What do you think? Okay. I did show this to you already, but, one is doing this is natural log of x plus 1 again. I could have done it with the Taylor series like we did first thing this morning, or I could have done, hey, I recognize this, and gone about it doing the geometric series and then integrating. There were options.
How would you know to integrate the geometric series?
How would I know to integrate the geometric series? Well, in creating this one, if I stop to look at it, like, that looks like that a over 1 minus r. So in doing the derivative here, be like, oh, looky, looky, they look similar. I'm gonna stop doing the derivatives because that's long. I'm now gonna do that series, but I didn't want, this was my first derivative. I don't want the derivative, so I need to integrate. Are you gonna see that? Never, never. Okay. See if you guys can try this.
Yes.
Are we supposed to know what it's saying there?
Are we supposed to know, oh, yes, actually you are supposed to know what it's centered at. This was buried in the first packet, so sorry. The words Maclaurin series. I made a better point of this sixth period. Maclaurin series means it's centered at 0. And just like all squares are rectangles, but not all rectangles are squares. Taylor series can be centered anywhere, including 0. Including 0. Taylor series can be centered at 0. But immediately they would have to tell you that created Taylor series created it or centered at 0 versus you can just say making Maclaurin series at some point. We'll be reading in about 15 seconds.